We present an internal learning approach to video inpainting. Video inpainting is the problem of synthesizing plausible visual content within a specified region. It has many practical applications, for example, to remove unwanted objects in the video. Traditional video inpainting methods rely on patch-based and flow-based optimization, which can suffer from distortion. More recently, learning-based methods have shown promising inpainting results thanks to the learned image pairs from a large external image video corpus. However, video data is more complex compared to image data, making it challenging to train a single model on an external dataset to learn effective pairs for general videos. In this work, we propose the first internal learning framework for video inpainting. Recent works in internal learning have shown possibility of capturing image pairs from the input image alone, which lead to many interesting applications. Different from this work, we study internal learning in videos under the problem of video inpainting. Our work is inspired by deep image pair. DIP uses a simple UNet architecture to map a uniformly sampled noise map to natural image by only minimizing L2 reconstruction loss inside the known region. The striking result of DIP shows that knowledge of natural images can be encoded through a CNN architecture. We start our exploration by directly extending DIP to video while only optimizing one model. We fix the noise map for each frame and map the noise to the video frames, using the same reconstruction loss on the known image regions. Without any loss constraining the unknown region, we get inpainted regions with high saturation contents. We further involve spatial temporal convolutions into the network by replacing the 2D CNN with 3D CNN. The inpainted regions are better constrained, but still lack of temporal consistency. Finally, we follow the trend of temporal coherent video generation by jointly predicting both frames and optical flows in two opposite directions. We apply L2 reconstruction loss and perceptual loss to constrain the known regions. We then propose the consistency loss by warping the generated frame via the generated flow to constrain the unknown regions in the neighboring frames. Note that to explore the extreme potential of the network, we intentionally restrict our final model only using 2D CNN. Our results show that it is possible to internally train a single frame-wise generative CNN to produce good video inpainting results that are spatially and temporally coherent. With the consistency loss, our final model can recover the occluded bench. Without consistency loss, the two baselines generate random stones, which is not consistent with the nearby content. To better understand how the model works, we visualize the encoded feature similarity between a reference patch and all the patches in other frames. A higher opacity patch indicates a higher feature similarity. We can see that the most similar patches identified by our learned feature are located on the exact same object across a long range of frames, which is important in ensuring long-term temporal consistency. On the contrary, the feature of a VGG model trained on large image datasets only captures general visual similarity and treats all the road bars as similar objects. We evaluate the video inpainting performance on real-world videos for object removal and composed videos for background completion. The quantitative evaluation on the composed dataset shows that our method generates more accurate and temporal coherent video inpainting results than all the baselines and most of the existing methods. Finally, we show the comparison with the existing methods. Our method, while only trained on the input video alone using a simple 2D CNN, can generate video inpainting results that are better or as good as the methods that either use handcrafted image patch pairs or pairs learned from external image video corpus. Our method can employ better natural image pairs to avoid shape distortions. When the input video contains significant lighting variance, our method still generates consistent results. Thank you.